Okay, so we're going to go over how to make a simple thread switcher. And we're going to be using this microprocessor simulator called Easy68K. You can see the name up in the upper left corner of my screen here, Easy68K. You can just type that name into Google and it'll be the first thing that comes up. It's a microprocessor simulator for the 68,000, which was kind of like it's a really old microprocessor. It was popular in the 1980s with the early Macintosh computers, and then it was abandoned in favor of the Power PC. But the thing is, this particular microprocessor simulator, Easy68K, is easily the best simulator I've seen, especially for people who are just sort of like just learning how to program an assembly language. Okay, so basically when you start it up, you're going to get a text file that'll sort of look like this. I've started writing some stuff in here already, but it'll basically be a text file with an empty template in it. Okay. And so, so you can see what I've done here is I basically pasted in all this stuff here. This is a big array that I've created, which is going to be the vector table, right? The vector table is kind of like it's a list of functions that get called during when certain events happen. Okay, so the first two vectors for the 68,000 is the first one is the initial stack pointer. And then the second one is the initial program counter. Okay, so we're gonna start executing code at the start, at the address of _start. That's going to be a function we're going to write. Okay, and the stack pointer is going to be there too. Okay, and this vector table is going to be located at address 0 in memory. Okay, that's what this org0 means. It means that this originates, I guess, at address 0. Okay, so the vector table for 68,000 is always located at address 0, and the first two vectors are the stack pointer and the initial program counter. Okay, and after that, I've put in a bunch of these dummy handler pointers, right? And so this is going to be a function that we're going to write that's basically going to be the interrupt service routine for every exception that happens. Okay, and you can see I've labeled each one of these things as each one of these vectors has a label next to it for what it's a handler for. You can just type in 68K interrupt vector table into Google and you'll see what the structure of this vector table is. So I just copied this off of a website that I found from Google. I didn't want to waste time in the video putting this thing together, but it's pretty easy to put together, right? So in 68,000 assembly language, I said that org is like an assembler directive that tells the assembler where to locate stuff, right? There's another one called dc.l. You see I've used that here, that basically allows us to define a constant, right? So you can use dc.l to define a 4-byte long word constant, okay? And every exception vector in the vector table is going to be 32 bits or 4 bytes, okay? And dc.l allows us to define a 4-byte constant. If we want to define a 2-byte constant, we can use dc.w. If we want a 1-byte constant, we can use dc.b. Right, and I'll talk about how to use that later. But most integers that we use are going to be long words, so we'll use dc.l. Okay. Okay, so this is the vector table, right? This is just a copy and paste thing, basically. So what we need to do is we need to define the stack and the start. Okay, so let's go down and do that below the vector table. Okay, so you can see that Easy68K has created start for us. I'll put an underscore in front of it because I'm calling my initial program counter, I'm calling it underscore start. You can see that Easy68K has put this org1000 statement in here. $1000 means that basically this is going to be a hex number, right? If we were just to say regular 1000 with no $, then this would be interpreted as a decimal number, right? But if we put the $, in front of it, that means that this is going to be hex 1000. Okay, so that's fine. We can put our program starting at address 1000 in hex, right? And so the start label is going to be located at address 1000 hex. Okay, and then we should also put our stack down here too. Okay, so let's make a stack. Okay, so we'll say stack, and then we'll say stack bottom, right? And we'll use a different assembler directive called ds.l, and this is going to basically tell us that it's gonna reserve storage for some stuff. Okay, so it's not actually going to initialize this the memory here. It's just going to reserve some memory for our stack in this case, right? So how much memory should we should reserve? Let's say 1 kilobyte up for the stack, right? So 1 kilobyte is 400 hex. So we'll have a 1 kilobyte stack, and put the stack pointer up here. Okay, so the stack pointer is going to start out at the top of the stack, right, at address stack bottom plus 400. And as we add stuff to the stack grows downward in memory. Okay, so it'll grow towards stack bottom. Okay, cool. All right, so we have all this stuff set up. One other thing we need to do is we need to create a dummy handler. Okay, and we will just we'll do that. Okay, and then I will in here I'll just make a tight loop that just branches back to start. So when the computer starts up, right, it's going to, when the 68,000 starts up, it's going to go to address 0, and it's going to read the initial stack pointer and initial program counter out of the vector table, and then it is going to jump to the initial program counter and start executing code there. And this BRA, this means branch always in assembly language for 68K. So basically, we're just going to keep branching back. This is an infinite loop that just keeps branching back to itself. Okay, except when an exception happens, if we get an interrupt, then we're going to jump down to this dummy handler, and then we're going to execute a no-op and return right away. All right, so let's run this real quick and see how it works. Hopefully, if this thing compiles. Okay. Oops, we got an error. Okay. Okay, so we got an error. Let's try and figure out what the problem is. Oh, okay, so this is the end directive. Okay, so we need to change the name here to end_start. All right, hopefully that works. Okay, no errors, no warnings. So if we just click the execute button here, then this is going to execute our program in the 68K simulator. And you see it's created a bunch of windows here, okay? So this first window here on the left side, this is the main code window, okay? And it's going to show us the assembled code, okay? So you can see the assembly instruction that we wrote. You can see the address where it lives, right? This is address 1000 hex. And then we also have the hex encoded opcode for this instruction. 60FE, I guess, must be branch to start, okay? Okay. And then, so then also we have our register file up here, right? These are all the registers. D0 through D7 are our data registers in 68,000. A0 through A7 are address registers, okay? So these address registers are going to be used for holding addresses in memory. The data registers are used to hold integers, okay? We have two stack pointers, right? We have the user stack and the supervisor stack. Okay, the user stack is for unprivileged code. The supervisor stack is for privileged code, right? So that's like the operating system. We have the program counter, which tells us the address of the instruction that's currently executing. And then we have the status register, right? So this should look fairly familiar if you've ever written assembly code for other processors like x86 or ARM or something like that. They're all pretty much the same, right? Yeah, so this is what we got here, right? And up on the very top here, you can see that we have, we can step through instructions one at a time, and I'll talk about how to do that in a second, right? Okay, so this is the simulator window. Then we have our hardware window. We'll go over that in a little bit. Let's just put that over the side for now. We have our stack window, which shows us what our stack looks like. And we can switch between the user stack and the supervisor stack if we want to. Okay, and like I said, the stack is basically going to start at a high address and grow downward, okay? And then we have our memory window, all right? So we can type in any memory address. Let's type in the address of the first instruction in our program. That's going to be 1000 hex. And what you can see here is this is the contents of memory, right? This is our This is our memory, right? So 60FE is the opcode for the first instruction. This is the branch to back to start. And then you can see there's a couple other instructions that live after that, and those are going to be our dummy handler, okay? Our no op and return from exception. Okay, cool. So, and you can see the opcodes are right here. So let's see what happens when we step, right? So if I step over, I can just keep stepping here, and this branch instruction is going to keep getting executed over and over again. Not a very interesting program, right? It's an infinite loop that only has one instruction, okay? So the thing that an operating system or a thread switcher relies on is basically the ability to use an interrupt. Okay, so we're going to use one of these interrupts in the hardware window here to create to basically make the scheduler out of. Okay, and we'll talk about that in a little bit. But let's go over what happens in a microprocessor when an interrupt occurs real quick. Okay, so if I click this interrupt button, interrupt 1, just once, okay, that's going to create an interrupt. Okay, and the next instruction that's going to get executed is the handler for that interrupt. Okay, this is the dummy handler, right? This is the handler for every interrupt on the system, right? It's encoded in this vector table, right? And when we click the interrupt button 1, that's going to cause us to jump to the interrupt handler for IRQ1, right? This is the dummy, and we've told it to, that's the handler is going to be dummy handler. Okay, so when I clicked interrupt button 1, it goes and looks in the vector table and checks to see, well, where should I go in the event that I get an interrupt 1? And it sees, oh, well, I'm supposed to go to dummy handler, right? And so here we are in dummy handler, right? When that happens, the processor is going to push some stuff onto the stack, okay? What it's going to push onto the stack is it's going to push two things onto the stack, right? The first thing is going to be the return address program counter, where it's going to go back to. Right? We need to remember where we came from right before the interrupt happened, so that we can get back when we're done processing the interrupt, right? And that's going to be address 1000. And the second thing that we need to push onto the stack is the status register. The status register kind of holds a snapshot of the outcome of the last instruction, right? So we have the condition codes here, which are like the outcome of the last instruction, whether if it was 0, or if it overflowed, if there was a carry out, all that stuff, okay? Now we have the interrupt mask flags, okay, which basically allow us to disable the interrupts or disable a certain subset of the interrupts. And then we have this other bit, the supervisor bit, which tells us if we are in supervisor mode, which is operating system mode, or user mode. If S is a 0, then we're in user mode, and that's like the regular software mode for this thing, okay? So the status register tells us sort of like what the mode of the processor was, and we push that on the stack so that we can sort of like remember how to get back to what we were doing before. Okay. Okay. So that's so we have, this is our interrupt stack frame. It's the 2000. That's going to be our status register. And 00001000, right? This is our program counter that we had before we executed the interrupt. Okay. Okay. Cool. All right. So then we're going to process the interrupt service routine. We're going to do a no op, which does nothing, and then an RTE is return from exception. What that's going to do is going to pop the status register and the program counter off the stack and go back where we were before. Okay, so this the stack pointer here is A7. Otherwise, you can look at the supervisor stack, and you'll see that when we pop this thing off the stack, we're going to add 6 to the supervisor stack pointer, and we're going to go back here. So this is our supervisor stack pointer, right? So we pop the program counter off the stack and the status register. Of course, nothing really changed here because the status register didn't have any useful information in it because we haven't really done anything the whole time, okay? But, if we were doing something important before that exception happened, then we would, we would retain the information that about the outcome of the last instruction, or if we were in user mode or supervisor mode before the exception happened, all that stuff. Okay, so what we can do here is we can even just set a breakpoint. If I click on the little green dot next to this no-op instruction, it'll set a breakpoint there. And then I can just, so that'll be a breakpoint at the beginning, the first instruction of the dummy handler. Okay, so I'm just gonna run, right? And this is gonna do nothing, right? This program does nothing, it just branches back to itself. But as soon as I click the IRQ button here, number 1, we're gonna vector over to our dummy handler, and we're gonna hit our breakpoint, and the simulator is gonna stop, right? And then we can just step through and keep stepping through. Okay, so basically I've just demonstrated this whole interrupt stack frame thing and the interrupt service routine. This is really the sort of like the main, this is the main sort of like the core of what an operating system does, right? It's the interrupts and the interrupt stack frame are sort of like used by the operating system to switch between threads or between tasks or processes, whatever you call that, right? So typically what happens inside of a processor is we have some kind of a timer which is going to interrupt the CPU. We'll say in this case you can program it on this hardware panel here. You can program it to interrupt the CPU every 100 milliseconds. Right? And that'll create an interrupt 10 times a second, basically. 100 milliseconds is a tenth of a second. Okay, so 10 times a second, we're going to create an interrupt. The interrupt service routine for that interrupt is going to run, and that interrupt service routine will switch from one process to another process, or one thread to another thread, and give it sort of like every thread that's ready to run fair access to the CPU. Okay, that's how we switch between threads. Okay, so let's get started. Let's actually let's make one of those things work. Okay, so the first thing we want to do is we want to set up the stack pointer first, right? Okay, so in our start program, for some reason it seems like our I don't know why this is, but the processor does not seem to be reading correctly the initial stack pointer out of the vector table at the beginning. So we're gonna set the stack pointer up by hand to begin with. Okay, so the first thing we're going to do here is I'm just going to move the initial stack pointer stack into A7. Okay, so this is A7 is the supervisor stack pointer. Okay, so we're going to initialize the stack pointer. Okay, and then let's create a couple of tasks, right? So, or threads, or whatever we want to call them. I'll call them tasks in here. Okay, so a task is just going to be structured the same way as a function, right? So we have task 1, okay, and that'll just be a tight loop the same way we made our initial start function, and we'll make task 2, same thing. Oops, okay, same thing. Okay, so you have these two tasks. They're structured the same way. They're just basically structured like functions, and it's just a tight loop that loops back on itself. Okay, task 1 and task 2. Okay. So, all right, so we have some code here that we can run. And what we want to do is we also want to create something called a task control block for each one of these tasks, right? So we have we'll make a task control block for task 1 and a task control block for task 2, right? And so a TCB, or a task control block, is basically just a data structure that holds some information about that task, right, for the operating system to be able to keep track of it. So let's populate this with some information, right? So what do we need to know? We're going to structure this like a linked list. Okay, we're going to structure the task control block like a linked list, right? So we're going to have a next pointer, okay, and a prev pointer. Okay, so we're going to use the dc.l directive here. to point to the next element in this linked list, right? So that'll be task 2 TCB. And the prev pointer is going to point to the previous element in the list. We'll make that null for now. I'll do the same thing here. Let me label these and comment these on here. So I'm going to make the next pointer null here, right? Because this is the end of the linked list. And we'll make the prev pointer point to the previous element in the list. Okay. And we will also create, we'll say the ready list. And we'll point to, this is going to be a pointer that points to the task 1 TCB. Okay, so we have a linked list here, right, where we have the head pointer, which points to the first task in our list, our first TCB in our list, right? And this guy, the first TCB on our list, has a next pointer that points to the next TCB, right? And the next, this guy is the next TCB. This is the last one, and its next pointer is null. Okay, this is the prev pointer for the first task in the list. So we should probably set that to be the list head pointer here. Okay, perfect. Looks great. So this is how you make a linked list in assembly language. Okay, so each one of these is going to be a 4-byte integer, right? dc.l creates an initialized 4-byte integer. Okay, cool. Okay, so we can have a couple other things in here, right? One thing we could do is we could have a task name, right? So right, so we have a name for task 1. So the way we create a string is we're going to use dc.b so to declare a byte constant, right? So this is going to be called task 1, and at the end, so this is going to declare a bunch of bytes, right? And at the end of this string, we're going to put a 0, which is our null terminator, right? And then we'll also have task 2 name. I'll do the same thing. Okay, so let's do the same thing down here. All right, so we have a name. And then what else can we have inside this task control block? We want to have a stack pointer. We should probably have a status register. Oops. Well, a status register, we'll put that. Okay, the task status register. We might want to have the tasks program counter. We'll put that, we'll just use the initial, we'll use the start of the function as this initial program counter. And that should be good for now. Okay. All right, we'll do the same thing down here in task 2. Perfect. Okay, so we should also create these stacks for task 1 and task 2. Okay, so let's do that down here. Okay, so we'll say oops. So we're gonna say ds.l, and we'll say 400. We'll make 1 kilobyte stack for task 2. Okay, and we'll do the same for task 1. Okay, so this is just going to reserve 2 1K stacks for task 1 and task 2. Okay, ds.l, define or declare storage or define storage. I can't remember what it stands for exactly, but basically we're going to allocate some storage. It's uninitialized storage, so we're just saying there's going to be a block of memory here. It needs to be 400 bytes long, which is 1 kilobyte. 400 hex is 1K. and the task2 stack is going to start high and it's going to grow low. Okay, and so we're going to use the task2 stack here. Okay, cool. So let me just try and compile this real quick and make sure it runs, or make sure it compiles at least. Okay, so we don't have any errors yet. Perfect. Okay. So now when we boot up, right, we got these two task control blocks that store information about each task, okay? And we've statically allocated them using these dc.l directives, right? So we know we have a next pointer for them, a prev pointer, right? We've organized this thing as a linked list. We could organize it as an array too, that will be fine. But I've chosen to do a linked list. And we have a name for each task, and we have a stack, status register, and a program counter. So it looks great, okay? So this is all the information we need to keep track of each one of these tasks, right? So now what we want to do is at the beginning of our, at the beginning of, at the beginning of our start function, I guess, right? What we want to do is we want to jump to the first task. Okay, so let's do that now. Okay, so we'll make a inside start here. I'll make another label, right? And we're gonna start the scheduler. Okay. Okay. So then what we're gonna do is once the scheduler starts, we're gonna get the head pointer from the linked list, right? We call that the ready list head. Okay. We're gonna get that ready list head into one of our address registers. We'll say we'll get it into A0, let's say. Okay. And then we want to, the other thing we need to do here, I forgot to do, is we need to make a pointer that points to the task that's currently being run. Okay. Oops, I just meant to say A0 here, not just 0. Okay. So let's create a cur task variable here. We'll say ds.l. Okay. So that's gonna reserve one long word or 4-byte pointer that points to the TCB of the task that's currently being run. Okay, so we need to initialize this cur task variable, right, in our start scheduler routine. Okay, so we will, oops, I'll do that down here, sorry. So we'll put that into A1. Okay, so we're going to get the address of the head pointer of the ready list into A0, and the address of the currently running task pointer into A1. Okay, and then what we want to do is we want to store the okay, so what we want to do here is we want to okay, so the first, okay, so A0 gets the, let's just say here, A0 gets the address of the first task in the list. Okay. But so that thing is going to actually the contents of A0, right? So that's going to be that's going to actually point to the contents of A0 is going to point to the head pointer of the list, right? So that's going to be the address of the ready list head. Okay, but what we want to do is we want to get the data at that address, right? That's going to be the actual pointer to the task1 TCB. Okay, so so what we'll do is we'll use a move instruction to get the data at that address, and we'll put that into A2. Okay, so A2 now holds the address of the first TCB. Okay, so that's going to be the address of the TCB for task 1. Okay. Okay, and then we'll get the cur task into A1s, right? So then what we want to do is we want to set the value of cur task to the TCB address here, which is in A2. Okay, so let's do that, right? We'll say, we'll put A1 into, oh, excuse me, A2 into cur task, right? A1 holds the address of cur task, and what we're going to do here is we're going to store the value that's in A2, which is the address of the TCB, into cur task. Okay. Cool. Okay. So now what we want to do is we want to get the stack pointer of the first task into the user stack pointer, right? So remember what we did before is we talked about the user stack pointer and the supervisor stack pointer. There's these two different stack pointers that are running depending on they're sort of like used separately depending on if you're in user mode, which is the regular mode of the processor, or supervisor mode, which is only really allowed to be used by the operating system. Okay, so we need to take the we're going to go look inside of our TCB of our task, right? That's going to be this data structure here, and we want to get the stack pointer for the first task. Okay, so that's going to be located at TCB plus 0, plus 4, plus 8, plus 12. So an offset of 12 from the beginning of this data structure is going to be the stack pointer for this task. Okay, so here we are. So so let's get that, right? So we'll say 12 plus A2, right? A2 holds the pointer to our TCB, right? And we'll get that into, we'll say A3, okay? So we'll say get the okay, so we can get the first task stack pointer into A3, and then we're going to move A3 into the USP, okay? So that's going to be the user stack pointer. Okay, and then the next thing we need to do is we need to get the program counter for this task. Okay, so let's go look in this TCB, right? This is offset 0, 4, 8, 12, 16, 20. Okay, so at offset 20 from the beginning of this data structure, we have the program counter, the initial program counter of this task. Okay, so let's just go, let's do the same thing we just did here, right? So we're gonna, oops, it could just be move.l. Okay, so we'll say move.l 20 from A2, and we'll put that into, let's say D0, right? Just doesn't matter what register we use, right? So we're gonna get the program counter. Right? We're gonna get that out of the TCB, and we're gonna push that onto the supervisor stack. And that's done like this, okay? So this addressing mode in 68K, if we put the minus A7 in parentheses here, that means decrement A7 and then move the contents of D0 into the memory at the new address of A7. Okay. Okay. So that's what we're doing here is we're actually creating an interrupt stack frame on the supervisor's stack. Okay. Right. just like what happened when we actually took a real interrupt. When we took a real interrupt, we created an interrupt stack frame. The processor created an interrupt stack frame for us automatically on the stack, right? Right now we're kind of making a fake interrupt stack frame that's going to have the address of the first test that's going to be run, and it's also going to have the what do you call this thing? The status register of the of our new task. Okay, so let's go get the status register. Right, where's the status register live here? Right, here's the status register. It says offset 0, 4, 8, 12, 16. Okay, so our status register is an offset 16 from the from the uh, from the beginning of our TCB. Okay, so we'll say move.w. We'll say 16 plus a2, and we'll put that into D0. Okay, so we use the move.w instruction here because the status register is only 16 bits, right? 2 bytes long, right? And a word in 68K land is 2 bytes, right? So you can say move.w is 16 from A2, right? But when we created the data structure, we used a long word to hold it, right? So this is we actually didn't need to use a full long word to hold the status register. We could have just said dc.w here. That would have been enough space to store our status register, but it's easier to just keep everything the same size, right? So we're wasting a couple of bytes of storage here by storing a 2-byte number in a 4-byte slot, but that's fine. It's not going to hurt anything. Get a lot of memory. So okay, so we're going to get the status register out of the TCB. Okay, let me put a comment here. All right, and we're going to push that onto the stack to create the second part of the interrupt stack frame. Oops, should be move.w though, right? Because we're trying to push a 2-byte word, right? To the stack. Okay, so now we have created this interrupt stack frame, and then all we're going to do here is use an RTE instruction, and that's going to pop the stack frame off of the stack and return to the address whatever we specified, which is going to be task 1. All right, let's try this out. Let's run this bad boy real quick here. So we don't have any errors. Good. Let's see what happens. Okay, so we start at the initial program counter here, start. Okay, we're going to put the stack into A7. All right, there we go. So here's our initial stack pointer is at 2034. Okay, that's the initial supervisor stack pointer. Okay, okay, and then we're going to get the ready list head address into A0. Okay, so let's just advance one time. So A0 stores the ready list head address. That's 2038. Okay, so let's go to our memory window here and put 2030 into the address here. And so what you can see here, this is 2038. This is the beginning of the ready list head variable. And you can see the value, the ready list head is 4 bytes long. It's a long word, right? Because we use a dc.l directive to declare it. And you can see that it stores this value 203c. Okay, so the ready list head variable points to 203c, which is that's the first task control block in our TCB structure, right? In our linked list, right? Well, it just so happens that 203c is actually right here. It's immediately after. It doesn't have to be immediately after the ready list head, but the way we wrote it, it was, right? So here's our TCB, right? So if we look back to the structure of the TCB, you can see the next pointer is 2054. That's the next element in our linked list. The prev pointer is 2038. That's the previous element in our list, or that's the address of the head pointer, right? 2038, right? And then let's see here. After that comes the pointer to the name 406C. That's the address of the name of this task. And then after the name comes the stack. Let's see here. 406C, it looks like, is also the stack. That doesn't seem right to me. I think there might be an error here. So let's take a look. Task 1 stack. Oh yeah, okay. So that's the initial stack pointer. It's right next to so the initial stack pointer of this thing is right next to the name. Okay. So the stack pointer is going to start here, but we're not going to actually overwrite the name if we push something on the stack. Okay. Okay, so the initial stack pointer is 406C, and then the status register is 0, right? That's the initial status register. And then the initial program counter is 102C. That should be the first address of our task 1. Let's see if we can find our task 1 here. 102C. That's the first and only address inside of our task 1 function. All right, so this looks good, right? And then the second task control block for task 2 is basically going to be the same. It's going to start at 2054 though, right? Which is down here somewhere. Okay, perfect. Let's do it. Okay, so let's do the start scheduler thing now. Okay, so we're gonna get the we got the address of our first task, right? Our ready list head, right? And now we're gonna read the value from ready list head, which is going to be 203C. That's going to be the address of the first task control block in our list. All right, so let's get that. So that's going to cause A0 to change to 203C. Oops, I'm sorry, A2. A2 is going to get 203C. This is the address of the first TCB. Okay, and then we're going to get the cur task into A1. That's going to hold the pointer to the task that's currently running. Okay, so then we're going to put the address of our currently running TCB, which is in A2, 203C. We're going to write that into the cur task variable at 2034. So let's keep our eye on memory. Here's 2034. I'm going to advance the program counter 1, and we're going to watch that number change. And there you go. 203C is now the cur task pointer that points to the currently executing TCB. Okay, perfect. Okay, so we'll get the stack pointer into A3. Okay, here's A3, 406C. That's the stack pointer. And then the next thing we're going to do is we're going to move that into the USP, right? The USP currently has this value here, so the next time on the next instruction, we're going to install the new user stack pointer. Okay, and we're going to install we're going to get the new program counter. Okay, and let's go to the stack now, and let's watch our stack. Here's our stack. So I'm going to advance the program counter 1, and you'll see the processor is going to push the value in D0, which is the initial program counter of our first task, 102C, right? 102C is the address of task 1. It's going to push that onto the supervisor stack. There it goes, 102C. And that's our initial stack, right? That's our initial program counter, right? So then the next thing we're going to do is we're going to get our status register into D0, and we're going to push the status register onto the stack. So watch this. Here we go. Push the status register. Looking good. And we're ready to go, right? So now when we execute this RTE instruction, that's going to cause us to pop the status register and the program counter off of the stack, and we're going to end up running code at task 1. So here we go. Bam, there we are at task 1. Okay, that is the basics of how you start a task in an operating system. Okay, so we got the first task running, right, which is great. That's actually pretty cool, right? So what you can kind of take away from this is that we used this kind of like a dirty trick, right? We used the RTE, or the return from exception instruction, to basically force us to return to a function that we were never really running in the first place, right? We created a fake interrupt stack frame on our stack, right? We sort of like made an interrupt stack frame by hand, right? Using these move instructions, right? We got the data out of our TCBs, and then we created this interrupt stack frame, and then we used an RTE instruction to return to that interrupt stack frame that we created, right? The interrupt stack frame has a couple of properties, right? So the first thing you'll notice on the interrupt stack frame is the supervisor bit. We intentionally set the supervisor bit to 0 in our status register, right? We did that because we want to return to running user code, right? Task one is a user level task, right? It's like a program that's running inside the operating system. So task one is running as in unprivileged mode in this CPU. Okay, so when we returned from our exception here, it installed this new status register, and it's going to force us to use the user stack pointer 406C, right? Instead of 2034. The supervisor stack pointer is different, right? So there's two stacks on this computer. There's a supervisor stack, which is used by the operating system, and there's a user stack, which is used by the currently running program, right? The currently running thread or the currently running task, whatever you call it, right? And every time we switch from one task to another, the supervisor stack is basically going to stay the same, right? We're always going to use the same region of memory for the supervisor stack, but every time we switch from one program to another, we're going to switch out this user stack. Okay? So that's what we're going to talk about next. How do we switch from one task to another, and switch the program that's currently executing. Okay, let's do that real quick. So basically, what we're going to use is we're going to use this interrupt, right? We're going to interrupt the processor every, we'll say every 100 milliseconds, right? And each time we interrupt the processor, we're going to we're gonna do one of these things. This is called a context switch, right? This is basically a context switch right here. Okay, there's a little bit more to it that but basically we're just going to save the currently running task's state. We're going to then go pick a new task to run. We'll restore that state basically the same way we did it here, and then we'll return from exception to the new task. Okay, let's do it. Okay, so the first thing we're going to do here is we're going to use a new interrupt. We're going to replace one of these dummy handler ISRs, right? So this one, IRQ1, is going to be replaced with the scheduler. Okay, so we're going to create a new interrupt service routine called scheduler, and that is going to handle IRQ1. Okay, so here we go. Let's put it down here and delete this. That was automatically added by Easy68K. Okay, so here's my scheduler. All right. Okay, so when we take an exception, the first thing we want to do when we take an exception is to save all the user registers, because we don't want to overwrite anything that the user was working on. If these tasks here, obviously these are kind of ridiculous because these tasks are not actually doing anything, so they're not using the registers. But in a real task, the user will be working with registers. They'll have important data in the registers that the operating system should not overwrite. Okay, so we need to save all the user registers somewhere. Okay, the problem is though, where are we going to save them? Right, we don't have any place we can really save them because we can't use if we use the registers to select an address to save these things, then we're going to overwrite the contents of the user's registers. So the best place to do it is just to save them temporarily on the stack and then figure out where to put them later. Okay, so the way you do that in 68K is you use a move M instruction. Okay, and we're going to this is the syntax of the move M instruction. Okay, and it's basically going to push all of the user registers D0 to D7 and A0 to A6, not A7, onto the stack. Okay, perfect. Okay, this is going to push them onto the supervisor stack. Okay, so now we saved all the users' registers onto the supervisor stack, and now we can overwrite our registers because we've already saved the registers, right? It's okay to overwrite them now. Okay, so now let's, what we want to do is we want to transfer these, the users' registers. We want to transfer them to the user stack temporarily, right? We'll save them on the user stack, and then the next time we come back to the user stack, we'll restore the registers from that user stack. Okay. Okay, so let's figure out where is the user stack. Where should we put them, right? Well, in order to figure out where the user stack is, we got to look in the user stack pointer, right? So we'll just use the USP. Okay, so we'll put that into A1. Okay, that's going to be the user stack pointer. Okay, and then we're going to we need to push the registers onto the user stack pointer. So this is a total of 60 bytes, right? It's I guess it's 15 registers, right? 8 data registers and 7 address registers makes 15 registers, 4 bytes each. It's a total of 60 bytes. So we want to subtract 60 bytes from A1, which is the user stack pointer, right? So we're going to subtract 60 bytes from A1, and then we will transfer all of the user registers to A1. Okay, so we'll say movem.l A7. Oops. Okay, yeah, A7 plus into D0 to D7. Okay, so we will pop the data registers off of the stack into D0 to D7. Okay, this is the supervisor stack, right? And put those in D0 to D7, and then we were going to store those onto the user stack, which is in A1. Okay, this should be move m.l. Okay, A1 has the user stack. Okay, let me comment this a little bit here. Okay. Okay, so here we push the user's registers onto the supervisor stack, and here we're gonna pop some of them, not all of them, off of the supervisor stack into the data registers. Okay. Whoops, it should be the supervisor stack. Okay, so we're gonna pop them off of the supervisor stack and put them onto the user stack, and then we're gonna do the same with the address registers. But there's only 6 address registers. We're going to store them in D0 through D6, right? Even though they're the contents of the address registers for the user program, but that's okay. We'll just store them in D0 to D6. Okay. Okay. And then we'll do the same thing. We'll save those onto the user stack. Okay. But we want to save them at an offset of 32 bytes, right? Because we already wrote D0 to D7 at the beginning, right? At the beginning of the user stack, right? So we don't want to overwrite them. We don't want to overwrite D0 to D7 with the address registers, so we will save at an offset of 32 bytes. Okay, perfect. Okay, so we've saved all of the users' registers onto the user stack. Everybody's happy. Okay, so let's see here. Let's do this. Let's get the current task here, and let's save the let's save the task state in the task control block, right? So the current task is going to be located in the cur task variable. Okay, so we'll get the value of the cur task variable into A0. Okay, and then what we need to do is we need to save the stack pointer, the status register, and the program counter all in this task control block. Okay, so the stack pointer is in A1, right? So we'll put A1, and we need to put that into the task control block. Where is that going to be located? This is at offset 0, 4, 8, 12. So it's going to be located at offset 12 from the beginning of the TCB. Okay, so we'll say 12 plus the offset of the TCB. Okay, and then we're going to then we need to get the status register and the program counter, but those are on the supervisor stack, right? Those are created those are on the supervisor stack frame. Okay, so we can pop those off of the supervisor stack. All right, so the stack pointer goes first, or excuse me, the status register goes first. Okay, and then we're going to put that into the TCB, and that's going to be located offset 0, 4, 8, 12, 16. It's going to be located offset 16 into the TCB. Okay, we'll pop the program counter off, and that's going to be located at offset 16, 20. That'll be located at offset 20 from the beginning of the TCB. Okay. Okay, so we're going to say this is going to be saving the processor state, or saving the task state. Okay, so we're going to put the A1 is going to be the stack pointer, right? We're going to pop its status register. And we're going to pop its program counter. And we're going to save the, whoops, I'm sorry. So we're going to put that into D0. We're going to pop its program counter, and then we're going to move D0 into 20 plus A0. Okay, cool. So we'll pop the task PC, save the tasks PC into the program counter, or excuse me, into the TCB, right? Cool. All right. So this is just called saving the context. Okay, this is just saving the current state of the currently running task. Okay, so now we need to pick a new task to run, right? So obviously we can use round robin. That's probably the easiest one, right? So that's just basically go to the next task in the list and pick that one. Okay, so that should be fairly easy to do, right? So A0 still points to the TCB of the currently running task. Okay, so what we want to do is we want to just get the next pointer from that one, right? So let's just go to let's go into A0. That's the next pointer, and we will grab the next pointer out of A0, right? So that's going to be the next task in the list. Okay. So now we want to check to see if that has a null pointer, right? If we're at the end of the list, if we're at the end of this linked list, then the next pointer is going to be null, right? In which case we need to wrap back around to the task 1 TCB. Okay. Well, yeah. Or the other thing we could do is we could just put task. Yeah, let's just put task 1 TCB in the next pointer here. Okay. Perfect. Yeah, that's perfect. Okay. So we'll just get the next pointer from our TCB into A0. Okay, and we'll store A0 into cur task. Right. This is we're replacing the cur task with the address of the TCB of the task we're going to run next. Okay. And then now all we have to do is basically just restore the new task's state, right? So we're just going to do the reverse of this stuff here, right? So we got to get the stack pointer, and then we got to restore the registers and build an exception stack frame, and then return. Okay, so first let's get the stack pointer, right? The stack pointer is located at offset 12, okay? In the TCB. Okay, and we'll put that into an address register, and then we will install, well, what we need to do first here is let's copy A1 to A2. I'll show you why we're going to do that in a second, okay? So basically A1 and A2 are both going to point to the registers for this task, the saved registers. The registers got saved on the stack, right? Okay, so so what we want to do is we want to point, and the registers take up 60 bytes, right? They take up 60 bytes of space on the stack. That's 15 times 4, right? It's 60 bytes. So 15 registers, D0 to D7, A0 to A6, that's 15 registers, right? So what we want to do then is we want to restore those registers, the saved registers, into the actual register file before we return. But we also want to put the user stack pointer in place. So let's point A2 past the registers. So we're going to add 16, or excuse me, we're going to add 60. Let's say 60 bytes to A2, right? This is going to be pointing past the registers, okay? And then we're going to move A2 into the user stack pointer. Okay, so now we're going to replace the user stack pointer with the stack pointer of the next task that's actually going to run. Okay, and then we can let's see here. Then we can restore our registers, I guess. Well, I guess we need to create an exception stack frame. Okay, so let's create the exception stack frame. Right, so let's get the program counter from, oops, that's going to be at offset 20, I believe it was, right? 20 from the beginning of the TCB. And we'll put that into D0, and then we'll push it. Okay, and then we'll get the status register out of the, I think that was an offset 16. Okay, so we're going to create the exception stack frame on the supervisor stack. Okay, then we're going to restore the registers, right? So then we'll just and then so the registers are going to come from A1. Okay, so we'll say okay, so we're going to restore the registers off of the user stack. The user stack pointer is in A1. We made a copy of it. Okay, and then we're going to return. Perfect. All right, let's see if this works. Ooh, man, I got a lot of errors here. Okay. Let's see here. Why doesn't it like this? Oh, it's because I put my minus sign inside the parentheses here. Let's see. Oh, okay. Oh, and then we got to use move M instead of move.l. So move M.l. So we restore the user's registers there. Okay, cool. Let's execute this guy. Perfect. Okay. So we demonstrated start scheduler earlier, so I won't go through how that works. But what I am going to go through is how to set up a periodic interrupt. Okay, so we're going to use this hardware panel over here. Okay, we're going to change the interval to 100 milliseconds. We're going to set it to IRQ1, and we're going to check this box here, which enables auto interval interrupts. Okay. Okay. So let's go. And then I am going to set a breakpoint at the scheduler. And I'm going to run this guy. Oh, and here we go. We took our first timer interrupt in the scheduler. So it ran through start scheduler to the RTE instruction, and we started executing our task 1, and then task 1 got interrupted, and we went to the scheduler. Okay. Okay, so let's look here. So first thing we're gonna do is we're gonna push all the user registers onto the stack. Okay. So here we go. So here you can see the supervisor stack pointer has been decremented, and we pushed all the user registers onto the stack. Okay. And then now we're going to transfer the user stack pointer into A1 now that we have saved our A1, right? That's 40C8. We're going to create some space below the user stack, and then we're gonna copy all of our registers off of the supervisor stack into A1. Okay, so A1 points to 408C. Okay, right now that's just filled with ones. Okay, and what you'll see here is this is going to move the registers from the supervisor stack into D0 through D7, right? So here you go. You can see that, well, it didn't change actually, but then we moved all the stuff from the supervisor stack into here, and now we're going to copy from D0 to D7 into the user stack, which is located here. So watch the memory panel here, 408C, it's going to be right here. You'll see it get populated with the user's registers. This is the user's data registers, which are all zeros, okay? And then we'll do the same thing with the user's address registers, okay? Those are going to go into the data registers here, and then we're going to save those. And you'll see that we, in fact, did do that, okay? Perfect. Okay, so now we'll get the cur task into a 0, right? This is the pointer to our currently executing task, all right? And then we're going to get the stack pointer. We're going to save the stack pointer, which is in A1, right? This is the stack pointer of the currently executing task. We're going to put that back into TCB, and then we're going to collapse the interrupt stack frame that got created for this task from the supervisor stack, and we're going to save that stuff into the TCB, and then we're going to restore the context for the next task. Okay, so this is basically what we're going to do is now we're going to go get the data out of, so we're going to go to the next task here, right, which is so in A0, right, 2098 has cur task. Okay, 20B0 is the TCB for the next task, right? That's the TCB for task 2. Okay, so we're going to install that TCB into the cur task structure, and then we will get the I guess this is going to be the, let's see, what do we do here? This is the this is going to be the stack pointer, I believe, right? I should have commented this. This is going to be the stack pointer for the next task, right? So this is going to go into A1, right? A130C8. We're going to copy that into A2. We're going to collapse the stack frame on A2. We've assumed that we stored the data registers there, right? And then we're going to put A2, the new user stack pointer, into the user stack pointer 3104. Okay. I see a bug here though, right? When we initialize the TCB, we should have initialized the TCB with a stack minus 60, right? Both of these in the TCBs here, these should have been initialized with the stack pointer minus 60. Okay. So let's go do that. Right? Because we need to allocate space on the stack for the registers. Otherwise, we're going to overwrite stuff. All right, let's try that. Okay, I'll step through this thing the full way here. Okay, so we'll go through start. We will go through the start scheduler thing. We'll get the ready list head. Okay, we'll get the initial stack pointer. We will install it, set up the stack frame and return from exception. Okay, and now we're going to be running task 1, and then I will manually create an interrupt here by clicking the interrupt 1 button. That's going to cause us to run our scheduler, and here we are in the scheduler. Okay, so we just did all this, so I won't go through and explain what's happening again. Okay. Okay, now we're at the point where we're going to start building the stack frame, the exception stack frame, right? So we're going to get the new tasks program counter into D0. That's going to be the address of the task 2, right? 108A, right? If you look down here, 108A is in fact the address of the first instruction of task 2. Okay, I'm going to push that onto the supervisor stack right there. There you go, 108A. There it is. Now we're going to get the status register, push that onto the supervisor stack, and return from exception. Whoops, excuse me. We have to first restore the registers here. You can see we did that. It looks like when we restored, looks like it didn't overwrite A1 though, which is strange. I don't know why it didn't do that. Anyway, here we go. We're going to return from exception, and now here we are down running task 2. Okay, it's perfect. And if we do it again, then here I'll create another exception here. It should switch back to task 1 if we do it again. Here we are back in task 1. So it's a round robin scheduler, right? It selects task 2, then task 1, then task 2, then task 1. Perfect. Okay. Okay, so one last thing I wanted to do to demonstrate this. So first of all, this is the kernel of an operating system, right? This thread switcher this is all an operating system is. It could be a little bit fancier, right? There's a couple of things we could add here. The first thing obviously would be dynamic memory management, right? So if we want to, the way we did it here, we have to create the data structures for the tasks before we compile it, right? So there's no way of adding or deleting tasks at runtime. So if we want to make this a little bit fancier, we could add a way of allocating new memory for a new task, and then or maybe deleting a task from the ready list or something like that to allow us to add and kill processes during runtime. Okay, but it wouldn't change the way that the actual data structures are set up. It would just allow us to sort of like dynamically change the tasks that are running, right? So that would be obviously the first thing that we would probably want to do. But yeah, this is basically all there is to to an operating system that's running on a computer, right? So one other thing I wanted to add here is the ability to print out some basically to print stuff out, right? So the Easy68K has this functionality where you can call you can use something called a trap instruction, which basically it's a special kind of instruction that's used to call the operating system. But Easy68K implements trap 15 to do some I/O stuff, right? And one thing that it can do is it can print characters out to this virtual terminal using this trap 16. Okay. Oh no, I guess it's trap 15 actually. Okay. Now you can look that up on Google. That they have some documentation for that, right? So what you do is you put the code of the trap that you want to um, the command code. You put that into D0. So the command for printing a null terminated string is 14. And then you just put the address of the string you want to print into A1, and then you just do trap 15. Okay, so this is the basic put S or puts implementation in Easy68K. Okay, so what we can do here is we can we'll just do a demonstration of this real quick, right? So I'll just okay, so this is going to be our message, simple OS booting up, and then $A, $D, these are the characters for return and a new line, carriage return and a new line, and then 0 is a null terminator. Okay, so what we're going to do is we're going to put OS greeting into A1, and then we're going to call puts. We'll do that in the start here. Okay, so let's just do this. Okay, so this is going to print the greeting. Okay, so let's look at the virtual terminal here. And if we run this, there we see when we called puts, it printed our little greeting here. Okay. Okay. And the other thing we can do is we can have it print. We can inside of our tasks we can have it print a different message, like a message that says task 1 is running now and task 2 is running now. Okay. Okay, we'll have another one that says task 2 is running. Just copy paste this. Okay. And then I'll just call okay, so BSR, if you didn't infer this, is it's the assembly instruction on Motorola 68000 for calling a subroutine. Okay, so BSR basically calls puts. Puts does this thing where it calls trap 15 and it goes back to, then it returns. RTS is return from subroutine, returns back to task 1. Okay, okay, so we'll do the same thing here in task 2, and then we'll have a little function delay that just delays for a while. Perfect. Okay. So let's see if this works. So it should alternately print out task 1 running, task 2 running. It looks like it's only printing task 1. Oh, I know why. It's because we didn't enable our interval timer here, right? So we were never actually running the scheduler. It was only running task 1. Okay, so here you go. So now you can see that it's alternatively running task 1 and task 2. Okay, so it'll run task 1 for a while. It'll run inside of task 1, it'll run that delay loop, and then the CPU will take an exception, run the scheduler, uh, you know, switch to task 2. Task 2 will run for a while, print out its message, and go back and forth. Okay, so this is basically all there is to, the internal workings of an operating system, right? This is a simple little thread switcher here. It just switches between threads. And basically, it's just using this. The magic instruction here is RTE, right? It creates a fake exception stack frame on the supervisor stack and uses this RTE exception to return from the fake stack frame to whatever place, whatever function it wants to return to, right? Okay, cool.